Welcome back. In this video, we're going to break down one of the most elegant results in financial economics, the idea that CAPM is not just a pricing formula but a complete structured model for how asset returns are generated. By the end of 8 minutes, you would understand exactly why diversification works and where it hits a wall. Let's start with a core question. Why does CAPM imply a factor structure? Recall that CAPM gives us an equilibrium condition. The expected return of any asset equals the risk-free rate plus a risk premium proportional to beta. Now where's the key insight? If CAPM tells us exactly what the expected return should be, then the actual return can only differ from the predicted value by some random term, a surprise. We call that a surprise epsilon I. That's how we get to our equation 1. Let's walk through the three founding equations carefully. Equation 1 defines epsilon I. It equals the actual return on asset I minus the risk-free rate minus beta I times the market access return. This is not an assumption, it's a definition. It's true by construction. Equation 2 is not just a rearrangement. We write Ri equals R plus beta I times the market access return plus epsilon I. So any asset return is decomposed into a CAPM predicted part and a residual. Now take expectations of both sides of 2 using the CAPM equilibrium condition. The expected value of Ri is exactly R plus beta I times the equity risk premium. This gives equation 3 and crucially, expectations of epsilon I equals 0. The residual has no average. CAPM has already accounted for all expected return. The second key property of epsilon comes from equation 4. Take the covariance of both sides of equation 2 with market return Rm. Covariance is linear and R and beta I are constants, so only the random parts contribute. We get covariance of Ri with Rm equals beta I times covariance of Rm with Rm plus covariance of epsilon I with Rm. Now we use two facts. First, covariance of Rm with itself is just variance Rm. Second, the very definition of beta I is covariance of Ri with Rm divided by variance of Rm. Substituting beta I times variance Rm equals covariance of Ri with Rm, which cancels out, leaving us with covariance of epsilon I with Rm equals 0. This is a crucial result. The residual epsilon I is uncorrelated with the market. Combined with its zero mean, epsilon I is genuinely idiosyncratic. It has no market component whatsoever. With both properties in hand, we can now write the one-factor model, our equation 5. This is arguably the most important equation in this section. Ri equals expected Ri plus beta I times f plus epsilon I for I equals 1 through n, where f is defined as Rm minus ERM, the market surprise with mean 0. Let's phrase each term. ERI is the expected return, your compensation for bearing market risk, fixed by CAPM. Beta I times f is the systematic component, your exposure to the common market factor. Epsilon I is the idiosyncratic residual, firm-specific noise with no market connection. The proof is clean. Substitute equation 1, expand, and everything cancels to give back equation 3. The model is self-consistent. Economically, F equals Rm minus ERM is called the basic source of randomness. It's the single shock that drives all an asset simultaneously. Each asset just loads on its different weight beta I. Now let's use factor model to decompose risk. Since beta I times F's and epsilon I are uncorrelated, we just showed that the variance of their sum is the sum of their variances. Variance Ri equals beta I squared times variance Rm plus variance epsilon I. The first term, beta I squared times variance Rm, is called systematic risk or market risk. It reflects economy-wide uncertainty. Notice it's proportional to beta squared. A high beta asset has large systematic exposure. The second term, variance epsilon I, is systematic risk, also called idiosyncratic, non-systematic, or diversifiable risk. It's the uncertainty that's unique to firm I. Here, the critical difference: systematic risk is present in every asset with a non-zero beta. You can't get rid of it just by holding more assets because the same market factor drives all of them. Specific risk, on the other hand, can be eliminated. This is where it all comes together. Equation 6 and the diversification argument. For any normalized portfolio X, the portfolio return has the same factor structure. Rx equals ERX plus beta x times the market factor plus epsilon x, where epsilon x is the weighted average of individual residuals. Now consider the simplest case, an equal weight portfolio where each weight is 1 over n. The specific risk of the portfolio is variance epsilon x equals the sum of I equals 1 to n of variance of epsilon I over n squared, which is at most Cn divided by n squared, which equals C over n. We use two assumptions. First, the individual epsilon I are mutually uncorrelated across assets. Second, each variance epsilon I is bounded by some constant C. As n grows large, C over n goes to 0. The specific risk of a well-diversified portfolio vanishes. But here's the wall. The systematic term beta x squared times variance Rm doesn't go anywhere. No matter how many assets you add, you're still exposed to market-wide fluctuations. That's the irreducible core of portfolio risk. Let me wrap up with the 4 big implications. First, because specific risk is diversifiable and systematic risk is not, rational investors who hold diversified portfolios face only market risk. Consequently, markets only price beta risk. Found specific risk earns zero return premium in equilibrium. Second, the diversification result is a theoretical foundation for index funding investing. Adding more assets averages away idiosyncratic shocks. Third, the market portfolio is the natural benchmark. The single factor F represents all the non-diversifiable uncertainty in the economy. Fourth, this one factor structure is the K equals one special case of Ross arbitrage pricing theory from 1976. APT generalizes to multiple factors. Think Farmer French with a size and value factor added on top. So to summarize, CAPM implies that every asset return is driven by one common market factor plus an idiosyncratic residual. The residual is mean zero and market uncorrelated. Total risk splits into systematic and specific components. Diversifications kill specific risk, but systematic risk is permanent. If you found this helpful, like and subscribe.